My name is Eve McDonald and I'm the EMESRT coordinator. I'm just going to cover the agenda for today's webinar and then we'll get into it. So I'll just cover some housekeeping very briefly. Part 1 will be presented by Tony Egan, our EMESRT Glencore rep, and Tony will provide us with a welcome and an introduction. Part 2 is the project presentation, and that'll be delivered by Dasan Gunasinghe, Mining 3 research engineer. Part 3 will be the question and answer session, and Tony Egan is going to facilitate that. Part 4 is the conclusion and next steps, and once again, Tony has put his hand up to do that as well. Okay, Tony, if you wouldn't mind, please providing us with a welcome and introduction.
Thank you, Eve, and good morning, good afternoon, good evening, wherever you are. We had about 30-something people this morning. We're up to 27 at the moment, so it's a good roll-up. So where do I fit in? Part of the EMESRT advisory group and involved in the vehicle interaction space in terms of leading that area with Matt Clements. Matt offers his apologies, and that's why I'm doing all the sections this afternoon. Unfortunately, Matt's had some technical issues where he is and got no signal. So I've also got another hat that I wear, which is involved in the ACARP, Australian Coal Research Projects, where we fund industry development within the Australian back coal industry. More often than not, that has an impact wider than just the Australian coal industry. I'm also involved with the ICMM Cleaner Safer Vehicles initiative in relation to vehicle interaction. So a few different hats. In terms of this project, its genesis was back in 2013. Ian Curran, who was with Rio at the time, he's now at BHP, walked in the door of the EMESRT advisory group and said, we've got a burning platform around this vehicle collision stuff. And at the time, we were talking about collisions and proximity awareness and all these sorts of things, and they're really controls. What we ended up defining was that vehicle interaction is the problem, and it's quite encompassing and quite complex. Through the course of that, we spent time working on trying to get the industry aligned on a definition of the problem, which sort of occurred through 13 and 14 and 15. And in about 2015, there was identified a couple of key issues that if we didn't come together as an industry, that the normal market forces would not address. And the first one of those was an interface protocol that involved being able to plug and play literally between different products and different machines so that there was no unique interface. And there's a couple of people on this call I recognise that they were in the original sessions back in those days. And we had quite a number of people. I think in the first phone call was 100, there was 70 odd in the room and about 70 online for the workshop that actually started to look at that protocol issue and about working together. And that brought third-party providers together with the OEMs and the users. So that protocol is now about to be published under ISO 21815. It's been a long and arduous exercise to get that to it, but I believe the 25th of May is the launch date for that. The second piece was this testing methodology, because when you look around the industry, or other industries, there are methodologies for commonality of approaches, so that as a user, when you buy something, you at least have some confidence or at least some understanding of the level to which a particular product has been tested. So this project was born back in about 2015 with the funding from ACARP, initial funding for phases 1 and 2. And Joel Koch, who's no longer with Mining 3, led those initial groups. Susan Grandin was the overall coordinator, but Joel did a lot of the work with the team. This part 3 that was funded a couple of years ago, a substantial amount of money, about $300,000, and then another 90 to get it to where it is today, began about 2 or 3 years ago. And this presentation today is trying to feed back to people within the industry who contributed along the way. Through EMESRT, we coordinated quite a number of workshops through phase 1 and 2, and also in phase 3. I mean, COVID's made it a bit more difficult, but anyway, here we are today. So Dustin and the team have done some great work, and certainly the feedback and the questions and the discussion this morning was very healthy, so that was great. We're certainly looking for any challenges, or people think yay or nay, because where this is going probably is towards the ISO group to look at whether this methodology could be included as part of the 21815 standards. So without further ado, I'm going to hand over to Dustin and let him run through things. You should have received a copy of the ACARP final report for this phase in your inbox in the last few days, hopefully. And you also would have received an invitation to access the sensor portal that's been put up, which is a bit of a resource about trying to understand those things. So Dustin's going to talk to some of that as well. So hopefully you did get a chance. Over to you, mate.
Great, Tony. Thank you for the introduction. I'll just share my screen. Eve, can you confirm that you can see that okay?
Yes, Dustin.
Perfect. Well, thank you once again, Tony, and everyone for joining this evening's session. It's quite an honour to discuss the outcomes of this current phase of work. So on behalf of the team, my name is Dustin Gussinger, and I'll discuss in an overview, a high-level overview of each of these outcomes. And before we begin, there's a lot of people I'd like to acknowledge and thank that contributed to this project, both current and previous phases, to really ensure that it has succeeded as it has done. So I'd really like to thank ACARP and then industry monitors, specifically Tony, Matthew Clements, Mark, Campbell, and Ian, without whom we wouldn't have had valuable feedback as we went throughout the current phase. I'd also like to thank EMESRT Advisory Group current and previous members. In terms of external collaboration, I'd like to thank Dr. Herman Emersma from the University of Pretoria, Professor Robin Burgess-Limerick from the University of Queensland, and Dr. Mark Dunn from CSIRO for their involvement in the current and previous phases as well. On top of that, I'd like to thank 3 anonymous PDS suppliers for the donation of their systems for this phase of work, as well as thanks to their site engineers for their help on the installation and the calibration. On our end of things, I'd like to thank our CEO, Professor Paul Lever, Susan Grandone, our COO and project leader, Dr. Isaac Patar, who's a work area leader here at Mining 3. I'd also like to thank Ian, Chris, Joel, and Eve as well for their involvement to the success of this project, as well as and all others that may not be listed on the screen at this moment in time. All right, so here's a brief overview of the presentation for this evening. So first I'll discuss some of the major project objectives, specifically targeting some of the objectives that we wish to attain in terms of the actual methodology's conception and some of the achievements as well. From here, I'll discuss the external collaboration outcomes, specifically looking at the user interface design, as well as the online toolkit that Tony mentioned previously. From here, I'll dive into the meat of the project, which is the capability assessment methodology development. And this involved really discussing some of the details around the test plan, as well as the data acquisition system that was developed to capture very valuable data, and then the evaluation portion of the project and some of the outcomes and examples from that as well. Finally, I'll conclude today's presentation by discussing some of the overall outcomes and recommendations regarding some of the remaining gaps going forward into future work. So the project objectives can be essentially divided into 4 main buckets, if you will. And if you can divide them into 2, the first 2 points really go towards providing guidance and knowledge in terms of UI design, specifically looking at the functionality and testing recommendations, as well as guidance and knowledge regarding PDS sensor considerations and sensors that currently are being used quite prevalently in the industry. So this involves covering some of those common sensor technologies and really focusing on that sensor fusion aspect going forward into future work. The second component is really looking at the development of a unified test methodology that involves looking at key factors that we could use to test generalized testing of PDS systems, as well as looking at prevalent scenarios that can then be categorized and developed into a test plan that can then be actually evaluated in a methodology. And this involves some independent review of some of the major scenarios that are currently documented in PR5A to be aligned into major prevalent scenarios for testing. Now, in terms of the methodology objectives, this also is divided into 4 main sections. So first of all, we wanted to obtain a realistic methodology to the scope that we could. So this really involved having the methodology be representative in terms of using representative vehicles. So in our particular case, we had access to a CAT 777 haul truck on site to be involved in all of the tests, and also show alignment to some of the more representative scenarios that exist in the industry and throughout most mine sites. which will show alignment to the PR5A documentation. We also wanted to make sure that the methodology was technically and physically achievable. And what I mean by this is twofold. Effectively, can the methodology be adopted at different sites? And also determining whether the methodology can be conducted under different PDS and still get the same amount of capability and performance understanding to be reported, and in terms of at least a baseline capability factor representation. Third is the efficiency of the test methodology itself. How long generally can this test take? From our test that we conducted in this phase, it was approximately 9 hours for all the tests, which I'll discuss in a bit more detail soon. So taking into account breaks and some repeat tests and variation, this was approximately 2 days per PDS unit, which is a great outcome. We want to ensure that the methodology was scientifically rigorous, and this involves ensuring that some of the tests are repeatable and ensures randomization to determine statistically significant findings. So from the external collaboration, as I mentioned previously, a lot of this focused on the user interface design. So this was a collation of findings from previous work that was conducted by Professor Robin Burgess from UQ, and includes the do's and don'ts of UI design, as well as some of the recommendations for improving UI. Specifically, and most importantly, it actually includes a lot of the operator feedback and adaptation into the suggested changes. So this involves that feedback loop going forward into future development. On top of that, it includes guidelines for handling change management in terms of deployment of these systems on the sites themselves, as well as any identifiable gaps and future areas of research that may still need to be covered. And in terms of the PDS sensor toolkit, so as Tony mentioned previously, this is now an online tool that's accessible to everyone in the industry. So I'm glad if everyone had a chance to have a look at that. So in essence, this is a collection of findings from Herman Hemmersma from the University of Pretoria. And in collaboration with Mining3, we put this into a digestible form in an online toolkit. In this toolkit, essentially it has key descriptions of each of the current prevalent sensors that are used in PDS to date. And this involves some of the working principles, discussions regarding its application to PDS, specifically looking at some of the advantages and the limitations of each of those sensors, as well as discussing the potential for combination of sensors in a sensor suite and some of the advantages and limitations there as well. So the early point of call for developing this methodology was really understanding what are these prevalent scenarios and how can they be adapted to be an efficient test plan in essence. So the first component of this was understanding an independent review of incident analysis and then aligning the summarized scenarios to the already existing immersed PR5A scenarios. So as you can see on the bottom there in that table, this represents the 6 main scenarios that we were able to highlight. So we have an intersection case, we have a work area interaction, we have tailgate or direct encounters with dynamic vehicles. We have something known as a static road hazard, which is effectively a dynamic object encountering a static object, either a light vehicle or a pedestrian encounter. And we also have loss of control, which is actually divided into 2 subcategories, this being either a void conflict or an incline or decline involving conflict with a dynamic vehicle. So focusing on that first row, we see nice alignment with the immersed PR5A scenarios, specifically the open cut surface mine scenarios. I've also added in a few extra different guidelines that exist at the moment in the industry and see how they also align with these summarized scenarios. So this allowed us to then categorize and develop specific choreographed tests that we could then evaluate for donated PDS. Now, the test plan specifically involved also highlighting some of the key baseline factors that may be involved in the outcomes and the performance of PDS. So this is really the distance between 2 objects, the speed of those objects, the actual object size, whether it be a light vehicle or a haul truck, and the trajectory that it takes. In this particular instance, we're looking at straight line or a slightly more complex curving maneuver. From the test plan, we've developed 3 major test types. So test 1 is a detection shape or zone classification test, which is represented on the right image. As you can see, this involved a haul truck statically situated in the center, while we had the light vehicle dynamically driving towards the haul truck at set speeds around the haul truck at set orientations. The idea being that the data analysis can show us what the final detection shape looks like and compare that to the expected outcome from that system. The second test is a more scientifically rigorous design of experiments test of those key factors I discussed earlier. So this is represented on the right as an example high-level overview. So as you can see, we've got an example here, the whole truck situated in the center, and we have a light vehicle traversing in either a straight line trajectory or a curved trajectory around two diameter radius circles. So the first circle is a short range test, and the outer circle is a farther distance radius test. And this is testing that distance metric. We also tested different speeds, and the object size is being tested by actually having the light vehicle and the haul truck switch places and having the other being dynamic. So in that particular instance, we'd have the light vehicle in the center and the haul truck being dynamic around the trajectory shown. A third type, which are the choreographed cases. So this is now specifically choreographing the scenarios to what we've discussed and identified as prevalent. So this involves a number of tests, ideally 6. And one of the examples you're seeing here is where we have the haul truck driving directly at either a light vehicle or a pedestrian object, in this case, which is a mannequin. Now, I'd like to really iterate safety as a key factor around designing these tests that we conducted. Looking at the example on the right, in this case, we ensured that there were stopping distances in place, everything was unmanned, and everyone was outside the exclusion zone in order to maintain high levels of safety. If we really point to test 2 now, if we look back on the image, as I mentioned previously, one of the factors is object size. So we needed to have the haul truck and the light vehicle effectively entering the center, and to make the test as efficient as possible, we choreographed it in such a way to maintain safety while the switch occurs, as you can see by the arrows indicated in the image. So part of this test methodology and procedure is the development of a data acquisition system. This effectively had some intermediate goals. One, to be open source so that it can be adopted at different sites, and to also maintain time synchronized capture of all the relevant information, specifically pertaining to the key factors that are highlighted earlier. So as you can see in the image on the bottom, this is our high-level overview of the data acquisition system we put in place. Now, the open source software we use is something called the Robot Operating System, also known as ROS. And what this allows us to do is run this operating system on multiple different computers that can then be mesh networked together and time synchronized together to record different sensor modalities. So going from left to right, we see the control center computer, which starts the recording process and the mesh network. We have the local object and the remote object, which is the haul truck, as well as the ute, having 2 independent computers on their own systems. And we also have an external computer known as bystander, which is then used to capture visual information through a stereo camera of the environment, as well as LiDAR information from the light vehicle, as well as an external camera as well. On top of that, we had other cameras to capture the test environment, as well as a drone to capture overhead views for further analysis if required. So here's a quick snapshot, really, of the data acquisition system. On the right, you can see an example of the LiDAR being used to determine the distance to a pedestrian object, and this represents the ground truth distance from the central point of the light vehicle. So this allowed us to detect pedestrian objects. On top of that, we had GPS modules on the light vehicle and the haul truck to gauge their position and speed, and this was independent to the PDS that was being evaluated in the test procedure. On the left is a snapshot of the actual evaluation process. So on the top right, we see a full model of our test pad, and we actually see the contour lines from the LiDAR emitting from the light vehicle, as well as some additional captures of stereo vision from the external camera shown with the blue haze, and we have a stereo camera located on the haul truck as well for redundant data acquisition. On the left, we actually see visual capture of those cameras, and what's not shown here, just for anonymity, but it's also importantly a capture of the interface itself from both the light vehicle and the haul truck to gauge what type of alarming is occurring and then categorize that with a position. On the bottom, we actually see a timeline of events of all the data that was captured from each of the 4 independent computers for data analysis. Now, in terms of the data analysis or evaluation process, as important as it is to capture, it is the baseline key factors. So the relative position and orientation between the local object and the remote object were captured via GPS. The relative speeds between the local object and the remote object were also captured via GPS, and then has LiDAR as a redundancy for position as well. And as I mentioned previously, that all-important visual and audio capture of the installed PDS interface was conducted to categorize the outcome to the operator with the current spatial position of the objects in the test. On top of that, we actually developed some scripts that ensured that we had more autonomy in the analysis process. That being said, a large amount of manual input is still required to categorize that visual outcome from the interface to the spatial information. Now, in terms of designating the outcome of the performance, this was conducted in a generalized way known as a alert type designation. So alert type 1 essentially corresponded to that initial detection. If there was no detection, then this alert type would never be triggered, and any higher level alerts would not be triggered. Beyond level 1 is effectively any type of audible or visual indicator that is then given to the user. So this allows us to quantify and at least categorize performance based on and see the differences between each system and even within systems as well. So the next few slides will show some significant findings from each of those three main tests. As you can see here, this is test 1, so this is that detection shape test. If we were to focus in on this first row, what we're seeing here is the outcome from the light vehicle's perspective on that detection shape test. So we have the light vehicle, once again, dynamic, and the whole truck static in the center, and the light vehicle is dynamic around the whole truck. So interestingly to note, we can see this is all from one supplier's unit. We can see on the left is a low-speed variant, with the middle being a mid-speed variant, and the right image being a high-speed variant. Now, I've categorized these as low, mid, and high to generalize that classification, because it could be dependent on the site that's being tested. For our cases, we had essentially lower speeds to test because of our site practicality, but this way we could designate this to be tested at more representative speeds if that site allows it. But what's interesting to note with these results is that you can see that speed is a factor in the system, as the higher speed alerts more in that higher alert types as we go into higher speed. If you look at the exact same scenario from the whole truck's perspective, we note that even for the same system, the amount of alert or alarming that occurs to the user is different based on which vehicle they're sitting in, even though the sensing system is exactly the same between the two. So that's interesting to find out from that particular system. We can also see that there's some inference of speed being a factor in those higher speed cases, with the higher alert type 2 being triggered more as the light vehicle is more dynamic. This is now an example of test 2. So just to reiterate, this is a design of experiments, a highly rigorous test. So what we're seeing here is just one snapshot of one iteration of a combination of those basic factors of speed, distance, and trajectory type and object size. So in this particular case, we're looking at the light vehicle being at the center, with the whole truck dynamic around the shortest radial distance, and then exiting to the left. So this is now the outcome from supplier 2. If we were to divide this into two, on the left is the outcome from the whole truck's perspective, and on the right is the outcome from the light vehicle's perspective of the same interaction. If we note them as rows, so A and B as one group, then C and D and E and F represent repeats of the exact same scenario at random events throughout the day or the 2-day period to understand any variation of that particular system. So we can see some slight variation, and that's something that we can comment on with this type of information. The other interesting thing to note is that this particular system is a very proximity-based system. You can see on the right, as the whole truck is dynamic and moving around the light vehicle's alarms actually trigger higher and then remain high as the whole truck is closer to that object. And you can see that reflected in the bottom layer of graph B, which is a plot of speed to distance, to relative distance as well. Now, what's interesting is if we look at the exact same scenario and exact same test for a new supply, this is now supply 3, we can immediately see there's some differences in the implementation of this system versus the previous one. And interesting to note, these two systems use the same sensing technology, but their outcome is determined by the way they've deployed their particular system's architecture. So again, on the left, we see the whole truck's perspective, and on the right, we see the light vehicle's perspective. Something interesting to note when we look at graphs C and D is that this particular system, while still proximity-based, prioritizes alerting at specific points in the interaction. You can see that there's higher alerts triggered when the whole truck is traversing in front of the light vehicle, as opposed to around its rear or in any other point in time. Conversely, looking at the light vehicle, we can actually see more detection in that frontal field of view, with some variation in alerting occurring as the haul truck traverses around the light vehicle. So now we're on to the last section of tests. So these are those choreographed tests. What's shown here is an interesting example where we have the haul truck statically situated, completely isolated, and then starts up with the PDS starting up at the same time. While this is happening, we actually position the light vehicle as close as possible to the haul truck to understand how long it takes for the PDS on the haul truck to alert the driver of an impending encounter. So if we focus in on the top row there, A and B for supply 2, A represents the light vehicle being close to the haul truck, and on the right, B represents the pedestrian object, the mannequin, being placed as close as possible to the haul truck on the front, the side, and the rear. Interestingly, for supply 2, we can see that the front has a faster detection for the light vehicle, with the sides and the rear being more consistent. And even more interestingly, on the right and in graph B, we can actually see that this particular system has a faster alert for a pedestrian. And this may be due to using different sensing technology for detecting that pedestrian, but it also ultimately boils down to how that system has been deployed. Because if we look now at supply 3, we see a more consistent detection of the object, regardless of whether it's a light vehicle or a haul truck. Interestingly, this system also had different sensing technologies used to detect either the person or the light vehicle. So even if that is the case, the overall implementation remains the same regardless for this particular system. Of more important note for this one is the long bars. So this represents the first point where an audible alert was detected from our data analysis, to then finally when a visual position was given to the user. So this is something interesting to classify as well for this particular system. This is another example from that test 3 range of tests. So this is the choreographed dynamic passing case. So what you see on the left is a low speed test for the haul truck and the light vehicle, both going at the lowest speed possible. And on the right is both vehicles going at the highest speed possible for supply 2's outcome. And again, we can see, as expected, that supply 2's system has speed being a factor. And what's interesting to note is these systems use GPS or GNSS-based sensing. So it wasn't expected to have speed as a factor, yet its integration into the system makes that key difference. Once again, just to note here, as mentioned previously, supply 2's system is purely proximity-based, and you can actually see that as the two vehicles pass each other and pass the encounter, the alerting can continue as well. Whereas if we now look at supply 3 for this particular case, especially looking at graph A and B, we see that this particular system, like mentioning previously in the design of experiments, tends to stop alerting after that encounter has gone past, or focuses on a specific point in time to encounter and alert the driver. Whereas once they're past that point, the alerting goes back to an initial detection of the other object. Also shown in addition is some variance testing that we've done, which is C and D. So this is where we have the haul truck and the light vehicle both going at different speeds, either a high speed or a low speed variant and vice versa, to ensure that the outcome remains similar. And you can see there's similar outcomes for this particular system going forward as well. So in terms of the overall advantages, as mentioned previously from the methodology objectives that we wish to achieve, we were able to obtain a realistic and representative test using real mine vehicles, as well as understanding some of the more key or prevalent scenarios that exist and showing alignment to the already existing PR5 documentation, as well as some other guidelines that exist in the industry to date. We also wanted to make sure that this was technically and physically achievable. To ensure that was done at different sites, what we did was we had collaboration with the University of Pretoria team, which implemented a first iteration of our test plan. And from the learnings of this, we implemented that updated version on site as well. On top of that, we were able to implement the test with different PDS units that were donated to us to understand whether the capability that's reported can be consistent and show some interesting outcomes as shown previously. Efficiency was also looked at in terms of the testing time. So as I mentioned previously, it was approximately 9 hours. So I have to point out this wasn't including the initial setup of the data acquisition system. This is purely testing time, looking at an effective window of approximately 2 days, including repeats and breaks for personnel. Finally, we wanted to ensure scientific rigor. And this was through our design of experiments testing procedure, which involved repeatable tests and randomizations to understand that variance in a particular system. In terms of limitations, there were six key prevalence scenarios that we wanted to tackle, but due to site practicality, such as not having a void available on site, as well as not having an incline, essentially limited us to the number of scenarios we could choreograph and test. A large component of that was also safety. So some of the intersection cases where we would have to have manned personnel driving these vehicles were omitted due to that safety concern. So something like this could be potentially done through simulation or other avenues as well, which could be a target of future work. The data analysis component, while there was some automation done in the scripting process, still involved a lot of manual analysis by looking at the visual and listening to the audio output of these systems, and then categorizing this to the recorded positional information from the GPS and LiDAR information. So some of this could be outsourced to a third party to make this more efficient. There could be even further automation development on these scripts to automatically detect visual information to categorize that as well. So that's something that could be done, but is very out of scope for this component of work. A key component of limitation in terms of this scope of work was that we only focused on that level 7 phase of work. So this is looking at purely that operator awareness level, looking at the outcome of the PDS unit to the operator itself, with some levels of level 8 being addressed, such as the decision being portrayed to the operator, but a large component of level 8 as well as level 9 itself was not addressed in this. And this largely involves the full system, and this was not available to us on site to really proceed with. And this presents a significant challenge because it does involve essentially testing not only the PDS, but the PDS with the collision avoidance system, its decision, as well as the vehicle's ability to enact that decision and categorize whether that was correct or not. So this may require simulation to do in a safe manner, as well as a practical environment that has the capability to test some of the areas that we could not do on our particular site. It also could involve less manned vehicles and more fully autonomous ones for that safety factor as well. And just a key point of note here is that the intelligence layer can be designed in different ways to effectively achieve a result, as was evident from the outcomes that I demonstrated in this presentation. Which also could present added complexity in validating some of these complete systems. So vehicle to vehicle and vehicle to pedestrian was considered in this particular phase. And unfortunately, we could not do multiple vehicle scenarios due to unavailability of multiple vehicles on site, as well as the complex nature of testing these reliably and safely as well. So this involves a gap going forward. Now, in terms of gaps, on the left, what we see is a summarized version of the gap analysis that was presented to the industry at the start of phase 3. So this is around September of 2019. And at this point in time, in terms of Mine 3, we effectively had an experimental design and theory developed, as well as a field test plan developed for inline parallel cases in terms of level 7 and level 8 and 9. But the actual instrumentation and hardware was not developed at this point. So the methodology was unable to be validated at this stage. And specifically, the detection and level 9 validation for more complex situations such as intersection and curves was not considered in this early phase. So I'm happy to say that this current phase of work has bridged a lot of these gaps. So if you look at that first row, inline parallel cases were tested successfully and were developed with the current experimental design and field test plan. The instrumentation hardware was developed to be able to test all the different complex types going forward, with the methodology being validated through this phase. I'd like to point out there are areas that are developed but highlighted as limited. And this is pertaining largely to that level 8 and level 9 out of scope testing that we did not do in this phase. So practically testing these safely is a large gap that needs to be addressed going forward. As well as more complex and dynamic multi-vehicle interactions. So while we were able to test curve scenarios, which are slightly more complex than the previous design, there are still more complex interactions such as transitioning scenarios as well that could be potentially tested. Thank you everyone for listening to this evening's presentation. I'm happy to field any questions.
Thank you, Dustin.
Tony, if we can just point out that we do have issues with our chat functionality. this afternoon. If we could use the raise your hand option, that'd be great.
Yeah, that's located up in the top toolbar.
Yes.
There's also some other emojis there if you care to congratulate people, etc., as well as raising your hand. So, well, we've got no one at the moment. Oh, Fabian's had a bit of a clap there. So Jeffrey's put his hand up. I'll throw it to Jeffrey then for a first comment or question.
Hi, good morning or good evening for you guys. Quite interesting presentation. Thanks all for the effort. I had a couple of questions on the findings examples. We see sensing results from different directions with their relevant alarms. Is the vehicle that has been equipped with the PDS, did you look at it from a direction trajectory independent perspective? Because if a vehicle moves, let's say, north, and there is a vehicle coming from the west, then what is the purpose of sensing that there is something on your left while that vehicle can't do anything with it?
That's a good question. So I guess to answer the first component, in terms of an actual direction, it was more about just the sensing around the object. So I guess north-west is sort of irrelevant in terms of the global direction, if that makes sense, just as a clarification. Yep. But in that particular instance, so one of the suppliers that we had, without disclosing more, was a vision-based solution. So This was kind of an interesting outcome because a lot of, I guess, the sensors that are, so that is part of one of the key sensors that we were able to discuss in the PDS sensor toolkit. And although GPS doesn't really require this as an issue, something like vision or even something that uses LiDAR or radar can have such issues like this where the field of view can effectively be obscured. So it's more to really understand that in terms of that detection shape test.
Okay, so do I understand correctly that the scope or the goal or the objective is to get the best, let's say, well, 360 and if possible even spherical situational awareness?
Yes, exactly. So it's supposed to be generalizable in the sense that people can reproduce this, if possible, at a baseline level and understand capability. So we wanted to ensure that at least different sensors can be tested and are covered.
Okay.
And it's not, I guess, set in stone. So those revolutions can be done in higher resolution, if that makes sense. So you can do a full revolution around the object as well. So there's room for improvement in building on that.
Okay. In one of the examples, there was GPS involved, GNSS. Mm-hmm. What happens? Did you consider what happens when that fails? Is that like a mission critical data set that is required for the exercise?
No, that's a good question. I don't think we looked at it in that much fidelity, I suppose. We didn't look at specifically dropouts or anything like that. It was more on the assumption that here's the system. Let's see if its expected capability matches what its actual capability looks like and what that actually looks like to the user, specifically the operator. Yeah.
Okay, cool. Then I got a few more couple smaller questions. Sorry for that. What was considered as the smallest mission critical object that needed to be detected?
So this was a pedestrian object. So it was like a mannequin-sized object, effectively, to the system that could potentially detect that. So all the systems that we had that were donated to us had the capability of detecting a pedestrian as well. And
at what distance was that required?
We didn't go with a specific requirement. Again, it's to keep that generalizable testing. Okay. So the idea is you could create a dialogue when you go ahead with these tests to define what that is, and then keep that as your minimum, and then set your maximum based on your site. So for us, that's why we went with designations such as minimum and max, or low and mid and high speed.
I understand. So, well, in Australia, I guess you don't have a lot of rain, fog, or snow or hail, but were these weather conditions considered?
Considered in the sense that they were documented if, say, a cloudy day was when we performed it, it was a cloudy, and if that had any effect. So on the outset, in that data analysis portion, we'd look at the outcome. If there was variance in some of the testing that was maybe done over a few days, and we'd then refer to that record of what the weather condition was like and comment on whether that was an effect or a factor. From these tests, we didn't note anything like that. Most of the testing that we did was on fairly clear days, so I guess we were lucky in that sense. But yes, this is something that could be potentially considered, but a lot of the times, it can or cannot be a factor. It's hard to really nail that one, if that makes sense.
Yeah, I understand. The last question. Prior to the live cases, has any digital sensor simulation been conducted?
No, we haven't actually, and that's something that could be interesting to go forth. I think it's sort of at an interesting point where you'd want to either consider a full simulation, but it also again depends on what type of sensing technology you could use.
Exactly.
So, for example, vision or LiDAR, you can do kind of a full visual simulation with some of the tools that exist in this current point in time. But then you could also involve a hardware in the loop type simulation where you'd have input to GPS signals being essentially replicated.
Yep.
So that's definitely an area we could look into for sure, and ensure some safety.
So,
okay, interesting.
Thank you, Jeffrey. Look, I think you've covered a couple of points where when we started this project out, you could spread it as far as you could think, and maybe not achieve anything. So the monitors actually provided some scope boundaries to the team in the early phases, and some of the things you've raised were actually talked about. But what was focused on was really to get that fundamental methodology in place, recognising that there would be variabilities as some of the conditions you've highlighted. So part of today is about getting some feedback and input about, well, you know, what does the next steps look like potentially in some of this research work. So thank you. Anybody else?
Thanks, Tony.
Thank you. Like to throw their hand up. If you don't, I'm going to nominate someone. So nominate someone. So this morning there was a question asked in relation to underground activities and where this sat in relation to that. And I see Brad Lukey's on the call. And Brad's been involved in the underground ACARP work in this space. Would you like to make a comment, Brad, in relation to the alignment?
Thank you for the handball, Tony.
Grenade.
Yeah, certainly. Look, I think the underlying philosophy behind the testing methodology is probably, I don't see that as dramatically different to what I see presented here. That they both come from a similar place. I guess from the systems that we've been testing of late, the main difference is the complexity. So in the case of what we've been doing, say, with shuttle cars, it's really quite a simple electromagnetic bubble that gets made around a machine. It moves much slower. You're not really as interested in the trajectory to something. It's more, is it within the bubble or not? So I guess it's far simpler in a lot of respects than the more complicated scenarios we need to deal with from an open cut perspective.
So the other thing I'll mention is that, you know, the ISO committee has, after working with them on the protocol, indicated that they'd like to see us bring forward something in relation to the methodology, and that they did ask for something that was both surface and underground. So the underground research team has been in contact with the Mining 3 group, and there's been some discussions. So there is some further work for us to do as to whether we could bring forward a single submission. Thanks, Brad.
No problem.
So Carl Hendricks, I see you're sitting there, and you've been on this journey for a long time. I think you're involved in one of those really early workshops I mentioned. Where are you? And you've been involved in some of the subsequent workshops along the way. What's your thoughts?
Yeah, it has been a long journey. I think I'm encouraged by the progress of all of this to an ISO standard. Caterpillar is really keen on the progress in this space, and we're working on getting an offering out in the market. It's still a bit early for us to be participating in edition, but this is certainly informative, and I think that I share your views that to complement the standard, the industry will benefit from a structured process for its validation. I also share some of the concerns of the earlier questions regarding the dependency on infrastructure and the importance of confirming their validity or their integrity. Often, the failure of these systems, there's just a lot that Caterpillar does, obviously, with autonomous vehicles that requires a very strong reliance on, radio connectivity, continuity of GPS corrections, and so forth. whether or not these are using a base station and things of that nature. So I think those are all additional important areas to validate that under ideal conditions, yes, this is good to see that when everything is working, this is how we can expect, these different solutions to work. But I think there's going to be equal concern for their dependence on infrastructure.
Certainly, I think it's some of the aspects of one of the reasons why the sensing portal was put together, to start to give people insights into some of the standard failure modes of things when you start, at that very base level. So I think that there's more to do.
Yeah, but certainly I think it's great progress on. I understand that it is phase 1, and we're interested in discussing phase 2.
Well, it's phase 3, so
sorry.
As you said, it's been a long journey.
Yeah.
So I see Niels has got his hand up.
Yes, Tony. Maybe not a question, but just a comment.
Yes.
In the underground environment, and we've been testing a lot in the underground environment, it's very different from the surface. We've tried to actually adapt our underground system for surface, but ended up with almost a totally different system. So we now have an underground and a surface system, which is different. So just to alert those that think they're going to test surface and just take the same system underground, it's not that easy.
Yeah, I think there's certainly a litany of experiences along that line over the last 10 years, Niels. I know certainly several companies that thought that could happen, and created them quite a bit of grief. So
that's correct. It's quite a road to go on. So, but we've been testing now underground for quite a few years, and we're now in our final demonstration phase for 3 or 4 mines currently, and it's going well so far.
Thank you. So I'm gonna throw to someone else who's been on this journey for a long time as well, which is Fabian Critter. I saw your hand flash up briefly there, Fabian, so I'm going to nab you for a comment.
Yeah, hello, Tony. Hello, everyone. Yeah, I can still remember the first meetings that we had. I don't know, remember how many years ago, 5, 6 years ago. No, I had my hand raised because I wanted to know why PDS1 was actually, supplier 1 was actually not mentioned, but it was already answered. I think that's a very interesting study that you have conducted. There is, as Geoffrey mentioned, a few things that need to be also looked at, as Carl mentioned. Very interesting with good findings. Now we need to look at also what about when we have 50 vehicles around, how all the infrastructure is handled, radio, or if you have actually Wi-Fi or LTE or whatsoever. There is more certainly to look at. Haven't read the report yet fully completely, but I will definitely have a look. That's very interesting.
Well, if you're having any insomnia problems, Phil Nelthorpe got halfway through it and put himself to sleep last night. So
Yeah.
It's a dry topic, no matter which way you look at it.
Yeah.
I take my hat off to the people who stuck with it. So thank you. Thanks, Fabian.
Thanks, Fabian.
So surely there's a few other people thinking about things. You want to ask questions, or you've got some thoughts about the future? No. Well, I think I've thrown enough people under the bus today. So, look, thank you, everyone. I might move to the wrap up. But if you still think of anything while this is happening, please throw your hand up. We'll keep an eye out. Look, thank you. What have you done there, Eva? There you go. Thank you, Dustin, for the presentation. And you can pass on our thanks to the rest of your team and in your organisation. Thanks to Eve for helping put all this together. And for those who didn't know, Eve now not with the Mining 3, but when she was with Mining 3, she was out there during the testing with a only high-vis vest on and a hat and up to her ear holes in it. So yeah, we've all had a piece of this project along the way. From an ACARP perspective, I think the monitors see that there is certainly, as highlighted by the group, some next steps, and we'll be capturing all of the questions that were raised today and pulling that together to look to have some discussions around what that next phase might look like, and that may involve another get-together of the working group, as the wider working group, and to, as we've done in the past, test some of the thinking on people and get some collaboration, so that, you know, whatever energy we put into things, it's focused and directed towards getting some real outcomes. So thank you for your time today.
Tony, just before everyone goes, I just
Yes.
want to just mention that the next EMESRT VI working group reoccurring monthly meeting will be held at 8 o'clock and 4 o'clock respectively on Thursday the 3rd of June. This webinar and this morning's webinar sessions will be posted on our website, and it'll be included as a resource on the VI Knowledge Hub as well. So keep an eye out on a link on our website if you want to revisit any of the presentations.
Thanks. So that's a good prompt, because the monthly vehicle interaction working group call is, I think there's over 150 people registered now. But if you usually get the minutes from Eve, but if you want to dial in, we basically cover a quick half an hour and sometimes less about what's happening in vehicle interaction related to issues from the ICMM to the ISO standards work, to this PDS testing work and other related activities. So if you're keen to keep in touch, it's 2 time zones once a month, 8 o'clock and 4 o'clock. I think we do it in Australia, so it covers everybody. So I encourage you, if you're interested, to get on those calls. So look, thank you very much. Have a great rest of your day or evening, or whatever suits, wherever you are. And thank you. And we'll keep an eye out. I think we'll be back in touch based on the results of the discussions today.